All right. Next, I want to introduce Mike Madigan. Mike Madigan received his BS in Mechanical Engineering from Clarkson University and has over 30 years of energy experience involving HVAC systems, renewable energy technologies, and waste heat recovery. He's a technical director at O'Brien & Gears Energy and Utilities Infrastructure Group. He's responsible for energy project development with a focus on industrial and higher education facilities. Mr. Madigan is a licensed professional engineer in the state of New York, is a lead accredited professional, and a qualified commissioning process provider. Mike?
Tough act to follow. Very nice. So O'Brien here has been involved in Onondaga Lake and the aquifer largely recently as a result of our involvement with the Honeywood project. Guy Swenson, who's here, he's been involved with it. Guy, you can raise your hand and wave around. He's really our senior geologist has been working on that aspect of it. My aspect is the mechanical thermal side of things. So we collaborate on this to kind of look at this one model of using the brine aquifer as a thermal resource. We were approached a while back by the Paramount Realty Group that's doing the Days Plaza project, possibly using the aquifer. Peter Cam was involved in those discussions, really trying to get, see if there was an opportunity to use the resource there. Historically, we believe that the Day Brothers department store used that resource as the NIMO facility did. That ended up becoming a nice sort of flex tech study that CDH Energy did, and subsequent to that, the project was pursued further. More recently, Sam Cosmano of IPD approached us and asked if we want to take a look at a similar application at the pipe block project that VIP Structures was developing on just a couple blocks up the street, and we were glad to do that. So that's sort of where we got started. For those of you who aren't mechanical engineers, we can talk about thermal and heat pump. This is sort of a cartoon to kind of help those that don't deal with these understand how the process works. So for an air-to-air heat pump system that works like an air conditioning system in forward and reverse. With the water source or ground source heat pump system, the heat exchanger that would normally be in the air rejects the heat to the ground. Now this shows the heating mode, which is the heat part of the heat pump mode. There's a heat exchanger and a circulating pump that circulates through whatever whatever water source heat exchanger you would have. This could be a ground, this could be open source water. In our case, it's going to be the brine aquifer. What it does is it pulls heat from the aquifer from evaporating refrigerant as a gas. It's compressed. It goes through a coil in the either air handling equipment or fan coil unit that provides heat to the building, and that condenses the refrigerant, where it's expanded through a thermal expansion valve, and then the process starts all over again. That's the heating mode. In the cooling mode, the process reverses. This is a reversing valve. Basically what that does is that reverses the process so that in the summer season, the heat that's the coil becomes the condenser, and the flow of refrigerant reverses. So this is cooled, it's condensed, it expands through the expansion valve, and then that expanded refrigerant gives up its heat of vaporization, which becomes cool air, and that's really how a conventional air conditioning system works. And then the cycle goes back to the compressor and starts all over again. So the key point we're looking at, this is conventional stuff over here. What we're really looking at here is doing something different than a conventional water source heat pump system where this is a closed loop inside a building with boilers and cooling towers, and then using the ground as the heat source for that. So, you know, these are some conventional loops. You'll hear folks talk about horizontal loops. These are shallow systems where that external loop is in the ground. These tend to be 4 to 6 feet deep in coils. Your commercial systems tend to be vertical loops. These could be 350 to 400 feet deep. The pipes go down and back up. They tend to be 3/4 to 1.25 inch diameter cross-linked polyethylene pipe that transfers heat very well. They're tied into multiple loops that become the geo-exchange system. And geo-exchange, ground source, heat pump, they're sort of terms that are generally used interchangeably. There's also pond-type loops. If you have surface water where, you know, basically loops at the bottom of a pond can be used to transfer heat. But these are all closed systems where the heat transfer fluid, which is typically water, doesn't come in contact with, you know, it isn't exposed to the ground or to groundwater. Open loop systems are really what we're talking about here today, and these could be in open bodies of water. You can see there's an extraction well, and then a reinjection well, and there's a separation distance, and that's the key. If they're too close together, you know, you don't have you've got short circuiting of your heat transfer. So there's some critical distances that vary with the types of systems that you're looking at. Obviously, open water bodies, you know, you probably don't need so much separation distance as you might in an aquifer. And the brine aquifer actually is a special case of the aquifer. You know, I like what Bill said. You could do this with freshwater aquifers too. We prefer to do this with freshwater aquifers, but the reinjection is more problematic actually than it is with brine. So that's the open loop system that we're really looking at here. So for the pipe lock system, IPD had a test well drilled, so we knew what the aquifer would produce at that location, and it produced close to 200 GPM, I think. We looked at being conservative here. The aquifer at that location is between, I think, 75 and 93 feet of depth. So we're looking at, we made some assumptions about what sort of flow we thought we could extract and then re-inject, and we came up with 110 GPM that seemed reasonable. For a geo-exchange, 3 gallons per minute per ton, that's a 10-degree delta T across the heat exchanger. We thought that looked reasonable, and that gave us a heat pump design capacity of a little less than 40 tons, which was enough to do not all the pipe lock building, but a reasonable portion of them. I think Sam's going to talk about what portion that was. The average aquifer temperature is 57.2 degrees F over the course of the year. And we assumed a volume at that location of about 20% water versus the rest would be solid. So for the flow and thermal model, you know, you can envision water flowing through this matrix of aggregate. Okay, the water flows, the aggregate doesn't. So we're looking at water flow. However, the aggregate has thermal capability as well. So that actually contributes to the thermal effect of the heat sink that we're trying to accomplish here. So just like any type of refrigeration cycle, in the cooling season, we're going to be dumping 125% of the energy into the brine aquifer that we're taking out. The difference there is you get compression of the compressor. In the heating season, we're going to be taking that heat out of the aquifer. Remember, the aquifer doesn't move, right? It's sitting there, as Bill said, it's stable. So So the heat that you put in, or in the summertime, is there in the wintertime to take out for heating. And that's how a heat pump system works, heating and cooling. So, so the heat that's removed is about 75% of the heat capacity that at design. And we looked at well spacing at 80 feet and 200 feet and 300 feet to see which values work the best. And obviously, the larger the well spacing, the better the performance of the model. So we ended up, recommending a 300-foot spacing for the best performance of the model. And here's kind of how the flow modeling looked. This is Guy's work. Thank you. Each one of these flows represents basically one path of many. It's continuous, obviously, but roughly each one of those flow paths is approximately an equal percentage of the total flow, say about 10%. So 10 to 12 GPM for each one of those flows. Obviously, these that are close up, their transport time is short across that 300 feet. Here, it's much longer. So these flows are based on the test well results. For this model, we assumed a single pump and a single injection well. And then we also assumed that each one of these flow paths was relatively equivalent. The model showed us that the transport time between the extraction well and the reinjection, or actually, between the reinjection and extraction, going this way, was between 24 and 300 days. So this short path is 24 days for water that's injected here to get to here and then give up its heat. When we're out to these further flows, this is more like 300 days, close to a year that it took for the water to come back. Just to give you a sense of what the flow looks like underground when you're doing this process. And with this model, we also looked at a number of equivalent full load hours during the cooling season and the heating season, but mostly the cooling season, to see how much this system would heat up the aquifer in this area. And it turned out it was conservatively about 1.7 degrees Fahrenheit for this whole area with the full seasonal operation. So not a lot, and we neglected any heat transfer that might occur around the perimeter, losses to the environment, and we also assumed that there was no transport at all of the brine aquifer, that this was steady state. And I think it's pretty stable, but even small amounts of migration, a foot or two a year, would have a big positive impact on the system performance. So that was our conclusion, that the 300-foot separation, that the project would work. And Bill, I think you covered these same things. There's environmental considerations to make this happen. EPA and DEC permitting requirements, which were really a surprisingly simple hurdle for the pipe block project. We were actually sort of surprised at how straightforward that was. There's fewer environmental concerns with drawing and rejecting from a brine aquifer than a freshwater aquifer. People are going to be drinking the water, they want to know what's going back into it, or are more concerned with it. There's more testing and quality requirements for re-injecting into a potable aquifer. And as Niagara Mohawk found out, surface discharges or storm or sanitary discharges can be problematic and expensive. So we prefer not to do that. So the aquifer, though, for this one project, okay, that it seems to work out pretty well. But as we think about where else this might work, we need to be thinking about what are the limitations of being able to use this resource on a thermal basis. So first of all, it's fixed. It's there. It's not getting any bigger. So its thermal capacity is finite. You saw the 300. You see the impact that even with 300-foot separation has on the adjoining areas. So interactions between sites is something that is going to be a consideration. The corrosive nature of the brine. Sam's going to talk about his heat exchangers and what they're made of, and they're not conventional construction. And then obviously on tight city parcels, drilling and getting access to the drill rigs for drilling the rigs is certainly a consideration. And then just having the separation distance between an extraction and a reinjection well is something that needs to be considered, particularly if it's on a single site. And Bill also showed that permeability within the brine aquifer varies from different locations. So where you are on the in relation to the aquifer is also going to be a consideration. So that's really the story of kind of how we looked at that and how we concluded that the pipe block would be a good opportunity. Looking down the road, other potential applications where this might work would be other downtown buildings with existing water source heat pump systems. New buildings as well, but even our corporate headquarters buildings got a water source heat pump system that we're actually going to look at the potential for having some supplemental cooling using the brine aquifer for our building too. Downtown buildings with existing chill water systems. You can use a heat pump with geo exchange to cool air. You can also use it to cool water in a similar fashion. And Bill, I don't know if Carrier's got any case studies yet, but
We've tested the DOT well, and we've got recommendations on what to do in the shells.
okay, all right. So I kind of I figured there would be some support for that. And then district energy. Obviously, we're looking at something on a larger scale than we're looking at for an individual building. There would be concerns about water flows and how much capacity you can get at a given site, separation distances, really all of the above. But there are, the Onondaga County District Energy System, is near to the corridor. Syracuse University is probably a little outside the corridor. One idea that came up was and we actually had looked at this with the Central New York Regional Planning and Development Board as part of the Regional Energy and Sustainability Plan was the Inner Harbor project. We've got all new construction right at the location of the aquifer, with seasonal heating and cooling, and it's not built yet. So this could be one where you could have perhaps some early at least feasibility thoughts about whether or not it could be a good application down there. So, but the VIP structures and IPD they've already put their money where their mouth is and started actually doing the demonstration project, the pilot at the pipe block project. And Sam's going to talk a little bit about that too.
Yeah. So,